Hello there, mathematical colleagues. Welcome to episode 20, the penultimate frowny face episode of Math 141 Summer 2020 recitation. Today, we are going to be looking at volumes using cross sections, and in particular, the volume of this solid is astronomical. That's a TikTok reference for those of you who are hip and cool. I suppose I should say for those of you who are not hip and cool and are not rocking the TikTok app and wasting far too many hours of your day on there. So we are going to be finding volumes using cross sections. This is a very nice application of the definite integral, which we discussed toward the end of chapter 5. And I think that we're just going to go ahead and get started with some problems. This is a relatively short homework assignment, only 9 problems. So I'm only going to do 3 of them. I figured it was fair to pick out 3 of them. So I picked one out from the 1 through 3 section, from the 4 through 6 section, and from the 7 through 9 section. 1 each, and we will go through and do those. These problems are all, just looking at all of the homework problems, they look quite similar. So my hope is that by watching just a couple of them here, you will be in excellent shape to tackle the rest. So problem 2 is what we're going to start with. Find the volume of the solid generated. One of the neat things about this section is that with these tools, you can start to discover some of the area formulas which you have come to know and love, or I should say rather the volume formulas, which I think is pretty cool. Y equals 0 and x equals 4. For example, I don't remember if this is an example in the book or not, but I distinctly remember using these ideas whenever I took calculus to find the volume of a cone. So I think that's pretty cool. The general formula, that is, for the volume of a cone. Anyways, so here we're going to be finding the volume of the solid generated by revolving this function, y equals 4x squared. By revolving, I did not write that correctly. This should say by revolving, I got distracted talking. The region bounded by these things, by the region, by revolving the region bounded by these 3 functions about the x-axis. Okay, about the x-axis. Whoops, sorry about that, guys. Okay. So whenever I get one of these problems, and in fact, this is similar to what I've said with regard to some other types of problems, the first thing that I like to do is draw a picture. And I am terrible at drawing pictures, so if I am saying you should draw a picture, you should probably draw a picture. So the way that this is helpful for me, let me go ahead and sketch it first, and then I'll explain why it's so helpful. So let's sketch our 3 curves here. Let's sketch those in, I don't know, we'll sketch them in red. That'll catch our eyes. So first we've got this function, well, we've got y equals 0. Y equals 0, that's just a fancy name for the x-axis, right? So that's just the x-axis. I don't really think I'm gonna try and somehow label that separately. X equals 4, so x equals 4 is gonna be like, I don't know. Let me make it a little bit further out. That'll make the rest of my picture easier to draw. Okay, so I don't know. This is, we'll say this is the line x equals 4, right? This vertical line out here. Let me label this as the origin then, just to be clear. And the other function which we have is y equals 4x squared. So before we even worry about revolving anything, let's just go ahead and jot down our regions. A loose sketch is perfectly fine. You do not need to capture anything super detailed here. Okay, so that is this function. This is y 4x squared. Oh boy, that is illegible. 4x squared, and that is this parabola here. So the area bounded by these regions, oh, my phone just went off. The area bounded by the region y equals 4x squared, y equals 0, and x equals 4 is going to be this green region here, right? So this is the region which we want to integrate, or the region, excuse me, which we are going to revolve about the x-axis. Now, I am not going to attempt to draw a picture of this, of how that might look. But just imagine picking this thing up and revolving it around this x-axis. So the formula which we're going to use, and this formula works anytime that we have something like this, is going to be that the volume, okay, V for volume, is going to be the integral from A to B of pi, and then we're going to have R of x squared. Okay, so R of x is supposed to be like the radius here. Okay, I hope this looks somewhat familiar to you, at least from perhaps some other example problems or Mackenzie's videos or the textbook. So A and B, let me comment on each of these things in turn real quick. So A and B are the bounds of our region. Bounds of our region. In this case, since we are revolving about the x-axis, right? That's what this says, right? Yeah, about the x-axis. In this case, they will be the x values. Because we are rotating about the x-axis. Okay, so in this case, we have, it looks like the x values bounding our region. On the left, we are bound by x equals 0. And on the right, we are bound by, and on the right, we are bound by x equals 4. So in this case, let me jot those down real quick. We're going to have A equals 0, B equals 4. Okay, again, those are just the x values which bound our green region. Pi, of course, is just a constant. The reason that pi is here, in fact, in general, this pi rx squared formula, this should look like the area of a circle, which you'll recall is pi r squared. And that's basically the idea which we are invoking here. So if that does look familiar to you, that is good. That is on purpose. My computer wants to update. I'm going to say do it another time because I am busy making a video right now. So let's see here. We've got A equals 0, B equals 4. So now we need to figure out what this R of x is. So R of x is a bit trickier to describe. So R of x is, and I'm going to, how do I say this? Is the radius of integration. I don't know if that's quite the right word here. But I think whenever I show you in the picture what it is, you'll see what I mean. Let me call this the radius of revolution. This is a totally untechnical term, which I am making up on the spot. But I think that whenever I show you in the picture, it will make more sense. So what I'm doing here is I'm rotating this, so like let's say, if I just look at this part here, say this cross section, I'm going to take this thing, this point here, and I'm going to rotate this graph. I wish you could see my pen right now, what I'm doing. I'm going to rotate it like up and around the x-axis, right? You can kind of hopefully see hopefully imagine that's kind of in 3D and kind of imagine what we're doing here. So the radius, about the length of the segments of which we are rotating, the lengths of those segments are given by whatever this value is, the height of this thing. Right? Like if I'm down here close to 0, well, I'm not going very far. So whenever I revolve, I'm not contributing much volume because it's so thin. Whereas up here, where it's thicker, right, where our function, where the cross section is bigger, we're going to contribute more volume here, right? And so this is the idea behind this R of x factor. With a circle, the radius is just some constant number. But here, the radius is changing based on our x values. So in this case, it looks like for a given x value, the height r of x is given by the height of this segment here. And for each x, that is just given by 4x squared, which is the name of our function, right? Y equals 4x squared. So the height, this value here, is 4x squared, it turns out. That's a difficult thing to explain, so I apologize if that isn't making a ton of sense. I think that the more you practice, if it's not making sense right away, I think that more practice will certainly help make that a bit more clear. This is certainly one downside of not being in a classroom. This would be much easier if we could be in a classroom together and potentially have some solid objects in front of us. But here we are in two-dimensional land, making the best of the situation. So now that we've got all our values, from here it's going to be fairly straightforward. We're going to plug them into our into our new fancy formula, and we're going to integrate like we usually have. So our bounds are a to b, and we know now that a equals 0 and b equals 4. I have this pi here. Pi is just a constant, right? So it's just chilling. And now r of x is 4x squared, and I need to square that. And then I stick my dx at the end. Well, let me see. I can pull that pi out front. Integral from 0 to 4. Whenever I square this, it looks like I'm going to get 16 x to the 4th dx. Right, when I square that. And this, let's see, this is pi. This is going to be 16 times 16x to the 5th over 5. Right, that's just a power rule exponent, or excuse me, power rule antiderivative. We're going to go from 0 to 4. That's kind of messy, plugging in x equals 0, or plugging in x equals 4. Then you're going to get 16 times 4 to the 5th, and 16 is 4 squared, so really that numerator is just 4 to the 7th. But I went ahead and worked this out ahead of time today. Look at me being proactive, and this comes out to 16,384 pi over 5. Okay, so let's recap real quick how we went about this. The first thing you generally want to do is draw a picture. That picture helps us later on whenever we try and find these bounds a to b, right? I'm sure we could have figured it out algebraically without a picture, but it certainly makes it easier to see, oh, okay, so we're going to integrate from x equals 0 to x equals 4. And I think even more importantly, it helps us see what this radius of revolution is going to be. In this case, we could see that it's going to be the height of the function, which is 4x squared at this point. Remember, that radius generally is not going to be a constant. Notice that's why it's written r of x, right? It's not just r. It's written r of x to emphasize that it is a function of x. And in this case, it happened to be the same function as this graph, this y equals 4x squared. Like I said, though, things can sometimes be a little bit different, so you do have to kind of understand conceptually what this r of x is. You can't just say, oh, it'll always just be whatever my function is. From there, once we've identified the value of our variables, we just plug them into our integral formula, and then we continue doing what we've been doing. Okay. Moving right along, we will now do problem 4. Problem 4 is certainly a little bit different. I think this will be a good one to contrast with the previous. So problem 4, basically the same instructions, but there is going to be one important twist at the end. Find the volume of the solid generated by revolving the region bounded by, this time I'm going to remember to write bounded by right here. Bounded by, and here are 3 functions. No, we got 4 functions this time. Holy smokes. We've got x equals 4y squared. We've got x equals 0. We've got y equals -8. and y equals positive 8 about the y-axis. So that is the main change here about the y-axis now. Okay, so let me emphasize that, the y-axis. Okay, so that we're going to have to take that into account. Let's go ahead and once again sketch a rough picture. Again, like I said, these pictures by no means need to be particularly detailed, but enough to give you a sense of what region it is you want to integrate over, enough to help you find your r of x, etc. Okay. Well, we have one of our bounding lines, our bounding curves is x equals 0. Well, x equals 0, this is just a fancy schmancy name for the y-axis. So I'm not going to attempt to draw that in there separately. Then we have y equals minus 8 and y equals positive 8. So let's draw in y equals negative 8 and y equals positive 8. Y equals positive 8. Let me go ahead and label this as the origin to be crystal clear. And so let me go ahead. So this one, the other function is x equals 4y squared. Well, if this was y equals 4x squared, then this would be a nice parabola facing upward, right? If this was y equals 4x squared. But since it's x equals 4y squared, so we've switched the value of the variables, right? We've switched x and y. What that does is that is going to rotate our function. So instead of a parabola facing up, we've got a parabola facing down, or a parabola facing to the right. I'm going to try and make it as symmetric as possible, because in fact that's going to be important here. Okay, I don't think that's perfectly symmetric, but you get the idea. In fact, why don't we go ahead and label these points? So this is the function y equals, where'd it go? X equals 2y squared. Equals 2y squared. So I know the y-coordinate of this intercept, this intersection point, right? The y-coordinate of this is 8. The x-coordinate is given by 2y squared. And y is 8, so that comes out to 128. Similarly, since we have that this function is symmetric about the x-axis, this is going to be 128 minus 8 down here. Okay. So the region, let me do something real quick. Oh no. Oh, bring that back, thank you. I'm gonna bring this label over, come on, give me the pen, thank you. I'm gonna bring this label over here. So the region which I want, remember that my fourth curve is the y-axis. So the region here is this region. So I've got this green region. Okay. Which again, I'm going to note that these two are symmetric. In other words, I'm saying that these two regions have the same area. They're just flipped. Okay, kind of looks like Minnesota, or at least it looks like the top of Minnesota here in this green region, the upper green region. So let me jot down our formula again, but I'm going to make one small change to it. So before, we had the volume was the integral from a to b of pi. Now here's a small change. Instead of r of x, this is going to be r of y squared dy. The reason for this, so if I'm rotating this, or excuse me, revolving this about the y-axis, that means that my radius is going to look something like this. It's going to be like that line segment, or that line segment, these new purple ones that I'm drawing. Right? It's going to be something like those line segments, because then I'm going to bring it around like this. Okay, again, that's poorly drawn, but I hope that you can at least kind of get the picture in 3 dimensions. I'm going to rotate this out around. It's coming out towards this, out of the screen towards you, and then goes back around to the left of the y-axis before returning to its original position. So in this case, we can see that our radius is given by a function of y rather than a function of x. Okay, right? Rather than a vertical segment of a certain length, this is a horizontal segment of a certain length. And in particular, we can see that that length is given by 2y squared. Right? That is this distance from the y-axis out to this curve. So this right here is r of y. Now, since we are integrating something with respect to y, since we are integrating with respect to y, how does that affect our bounds? Respect to y, that means that our bounds are going to be y values. Our bounds must be y values. Okay, and we need to be careful here. At first glance, and this isn't, in some sense, this isn't quite incorrect. In some sense, it certainly looks like A then is -8 and B is +8, right? Because I see that this lower endpoint down here, the y coordinate of this bound of this curve is -8, and up here we have +8. So it looks like I want to go from y equals -8 to y equals +8. And we absolutely do. But here's the thing. Well, actually, why don't we go ahead and integrate it this way? Let's go ahead and do it this way, because I want to help, because I want to help see, again, this is not, in some sense, this is not incorrect, the way that we're setting it up. But it's going to remind us of something that we need to be careful of. So let's go ahead and compute our volume. So our volume is going to be the integral from -8 to +8. So I've still got this pi here. And now r of y, we said was 2y squared, right? We kind of had that discussion. So pi times 2y squared dy. So this is pi times the integral from -8 to 8. That looks like 4y to the 4th dy. And that is pi times 4y to the 5th over 5. And we're going to evaluate that from -8 to 8. Oh, wait a minute. I thought that we were going to get something wrong, but actually this is going to work out beautifully. I'm sorry. I am tired, and I am realizing now, okay, so this is actually going to work out fine. So this is going to work out perfectly fine. Let's go ahead and finish this thing up. Well, 8 to the 5th is, so this is going to equal pi times, 4 times 8 to the 5th over 5 minus 4 times -8 to the 5th over 5. That's another beast, just like the previous one, that, quite frankly, that is going to be difficult to compute by hand. What I notice here, though, I will point out, and this is where I thought things were going to go wrong. I thought that things were going to go wrong because I thought that what was going to happen was we were going to end up subtracting off the same thing. I thought that it was going to be one of those situations where you have to take absolute value into account, because I thought we were going to subtract out the bottom area because it's below the x-axis. But now that I think about it, yeah, that's actually not an issue with this type of problem, so I apologize. I can explain to you how I did it, because I did this one ahead of time as well. So I can explain to you the other way that you could do this and get the same answer. Anyways, what I did here, well, -8 to the 5th, since 5 is an odd power, -8 to the 5th is going to be a negative, is going to be negative. So now I have a negative combined, I'm subtracting a negative, so that just becomes a positive. And this one I also worked out ahead of time. It comes out to 262144 pi over 5. Okay, so let me tell you what I had been thinking. Alternatively, what color do I want to use for this alternatively? So let me just draw the little line here. Alternatively, what I could do is I could only integrate, I could take a to be 0 and b to be positive 8 and multiply the integral by 2. Multiply integral by 2. The reason that this would work is because of that symmetry which we pointed out earlier. The area beneath the x-axis matches that above the x-axis exactly, right? These two things match, these two areas are the same. So if I only rotated this top half from 0 to 8 and then doubled it, that would give me the exact same thing. However, either way works fine. Truthfully, I would probably have done it the a equals negative 8. The first, I would have done it the way that I actually solved this one here, because that's more straightforward. However, I thought I was going to have an issue when I did this ahead of time, but I did not. But if you're feeling cheeky and you want to use a cute little trick, you can absolutely do this with this symmetry. Okay, this final problem, again, is going to be slightly different. Still, there are 3 parts of it. I'm only going to work out one part of it, because as I said before, I think that once you understand the first part, you can apply those exact same ideas to the second and third parts. So this is the final problem on the homework and the final problem of this video. Find the volume of the solid generated by revolving the region bounded by the parabola, y equals minus x squared over 9, and the line y equals negative 1, y equals negative 1, about the following lines. And actually, I said I was going to do part A, but now that I look at it, I think that part B would be more interesting. So I'm going to do part B instead, and I will leave part A to you. I think that part A is more similar to what we've done previously in this video. So in part B, we want to revolve the region about the line y equals negative 2. So in the previous 2 problems, we revolved our regions about axes, the x-axis or the y-axis, but here we're taking a slightly different twist. We are instead going to revolve about the line y equals negative 2. So the formula is not going to change too much, okay? The formula will be very similar, but we are going to have to make some changes. So let's go ahead and sketch everything that we need. Let's sketch the line y equals negative 2 down here. So this is y equals negative 2. That's the line that we're going to rotate about. Okay, in fact, let me switch colors for the other parts. Then we're going to have y equals negative x squared over 9. Oh boy. Well, I don't know exactly what that looks like, but thankfully I don't need to know exactly what it looks like. What I need to know is that it looks like it's going to be a parabola, which opens downward because of the negative out front. And I know that it's going to have its vertex at the origin because we haven't shifted at all. We've scaled a little bit with the division by 9, and we flipped it with the negative, but we have not shifted at all. So that's going to look something like this. I don't know. Again, does it matter how exactly we draw this? No. The important thing is that we get the general shape of it, i.e. this parabola. So this is y equals negative x squared over 9. That's this guy. That should look like a 9, not a g. And now the other bounding curve is the line y equals negative 1. So that means that our area, the region which we want to integrate, we want to revolve, is this region here. Okay, so we need to be a little bit careful here. This is going to make use of a second formula, which is quite similar to the first one. This is going to be a washer problem. I hope that sounds at least vaguely familiar to you. So in this case, the volume, well, we're again going to integrate something from a to b. We're again going to have a pi, but now we're going to have a slight change. We're going to do big R of x squared minus little r of x squared dx. Excuse me, that square, that should be just with the little r, like that. Okay. So let's think about this for a second. Little r is going to be, so the way that you should think about this is I've got, so the kind of this gap, right? You see, we've got this gap here between the line about which we are revolving, the axis of revolution. We have this gap between that and where our region starts. And this gap, whatever this is, this tells us, this gives us our, oh my gosh, this gives us a small r. So this tells us what the small r is. Okay. Let me think about this actually. It might be easier. I'm trying to see if the textbook recommends doing it this way or recommends, because there are two ways that we could do this. We could stick with the line being y equals negative 2, or we could, let me think about this for a second. No, that's okay. Yeah, this will work just fine. Okay, so little r in this case, I'm going to have to be careful here. Little r of x, well, this is, again, this is the length of the gap, okay, kind of the hole in the washer, if you will. In this case, it looks like that's just 1, right? It looks like the length of that is always given just by 1. Okay, so in this case, we're just going to have r of x equals 1. Okay, again, the reason for that is that no matter what x value I'm at here, right, whether I'm here, or whether I'm here, or whether I'm here, the height of that gap is always 1, right? Now, we need to find the height of, we need to find big R. So big R of x is, again, kind of like before, it's going to be the length, how do I want to say this? The length of the outer radius. And the textbook calls the gap here, kind of what I'm talking about here, they call this the inner radius. Okay, so in this case, the outer radius, it looks like what it does is we go up 1 here, right? We're going up. So basically I want to know, what is the formula for, if you give me an x value, what is the formula for the length of this thing here? Well, it looks to me like it is going to be, so we've got 1 because we've got this x, we've got this extra segment 1 here. So this gives me a 1. And then the second part looks like I am subtracting, or it looks like on top of that, I'm going to go, how far extra am I going to go? It looks like I'm going to subtract out, excuse me, it looks like I'm going to add 1 minus x squared over 9. Let me see. Yeah, let me do it this way. I'm going to totally dismantle this. So I apologize for that. But I think that it will make things more clear. Yeah. So I'm going to leave this here. Actually, I'm just going to put a big X through it. What we had was not wrong there. However, I think that the way I'm going to present it now will make more sense. So let me just real quick get our picture down again. I apologize for the delay here, but I think that this will be worth our time. So this is y equals -2. This is y equals -1 here. Okay, y equals -1. And then we had our other curve, which looked like this. Okay, so this was our region. And this was y equals -x squared over 9. So here's what I'm going to do. I could revolve about the line y equals -2. But that required lots of hard thinking. So what I'm going to do is I'm going to translate everything up 2 units. Translate everything up 2 units. Okay? So all I'm going to do is I'm going to draw the same picture, but now my axis of revolution is going to be the x-axis. Because what I'm doing is I'm just going to move everything up 2 units so that y equals -2 gets moved to the x-axis. The line y equals -1 will get moved to the line y equals +1. Right, so this is line y equals 1. And then -x squared plus 9 will get moved up here, or -x squared over 9 will get moved up here to y equals -x squared over 9 plus 2. Okay, now you're probably asking, well, geez, that doesn't seem like it was very helpful because I still have to do the same thing. All right, we're still going to have to integrate and all that stuff. The benefit of this is that now all that I have to do is revolve about the x-axis, which is going to make writing my formulas so much easier. So now we're going to revolve the green region about the x-axis. And here's why I have not done anything illegal. suppose that I have, I don't know, pick your favorite solid. Suppose that I have a baseball. Okay, I'm a baseball fan. So suppose you have a baseball. No matter where I move that baseball, its volume is the same, right? No matter where you put it in the whole universe. Maybe there are places in the universe where things get funky. No matter where on Earth you put it, the volume is going to be the same. Well, all that we've done here is we've taken our baseball, or in this case, perhaps some more strangely looking shape, and we've just moved it up in the plane. That's all that we've done. So moving it in the plane isn't going to affect the volume, so long as everything moves, right? We've moved our axis of revolution, and we moved all of the relevant functions. So all that we've done is I took this picture here, and I cut and paste everything up 2 units. Okay? So now we're going to revolve about the x-axis, and this is, oh my gosh, I can already see how much easier this is going to be. So again, the volume is going to be the integral from a to b, pi, and we had r of x squared minus little r of x squared dx. Again, let me jot down, no, I don't want you, I want, so little r of x equals the inner radius. Okay, and in this case, we can see very clearly that the inner radius, this height here, is just given by the function y equals 1, right? Because it's just given by this curve. So this is just given by 1. Just as that part is basically the same explanation as before. But the second part is what is going to be massively easier. Big R of x is the outer radius. And in this case, now I can see that the height of that like this height, is just given by this function, y equals negative x squared over 9 plus 2. Okay? Because since I'm starting at the x-axis, when I go up here, this distance is exactly equal to whatever y is equal to. So in this case, r of x is just minus x, oh, let's switch back to blue, minus x squared over 9 plus 2. So now let's go to our integral. Okay, so I have the volume equals, okay, well, let's figure out what a and b are. A and b are going to be the x values of these 2 intersection points. Well, I know at this intersection, at both of these, that y is equal to 1. So what I can do is I can say, well, 1 equals negative x squared over 9 plus 2. And this turns out to be negative 9 equals negative x squared, which means that x equals plus or minus 3. If I went through that algebra a little quickly, I apologize. You can take a minute and check me if you need to. Okay? So x equals plus or minus 3, which means that this intersection point is given by 3, 1, and this intersection point is minus 3, 1. So now whenever I go to integrate, integral from minus 3 to 3, we could invoke symmetry again here if we wanted to, but we won't do that here. Okay, so r of x squared, okay, so this might get a little bit messy. Negative x squared over 9 plus 2 squared minus, thankfully, little r of x is just 1, so that's nice and easy. That's just minus 1 dx. Okay, let me pull this pi out front. Integral minus 3 to 3. Okay, square the first, and I get x to the 4th over 81. Double the product, so that's minus 4x squared over 9. Square the last, plus 4 minus 1 dx equals pi integral from negative 3 to 3. X to the 4th over 81. Okay, this is just going to be applications of power rule now. So in fact, I'm going to get rid of that, and I'm just going to combine this plus 4 and minus 1 as plus 3. So this is going to be pi times x to the 5th over 81 times 5 minus 4x cubed over 9 times 3 is 27. And then plus 3 is going to become plus 3x. And I want to evaluate all of this from minus 3 to positive 3. I'm going to go ahead and leave it there. You are capable of plugging in these numbers, and I think that you can figure it out from here. But let me again reiterate. In fact, I guess it's kind of a good thing. So what we did here, this was not incorrect. Okay, this first mess that I got myself into, there was nothing incorrect about it. However, when it came time to try and figure out what the formula was for, to find out what the formula was for big R of x, it became a little fuzzy because I was down below the x-axis, right? So like I know, like I could have figured out, well, okay, this height here is negative x squared over 9. But then I need to deal with this negative 2 down here, and things kind of, I mean, we could have worked it out, sure, but it kind of was a little bit messy. I found it easier to translate everything. Okay, so we started with this picture, and then we translated everything to the x-axis, which made our formulas much nicer to work with. Okay. So the idea here, the reason that I chose 2 units was to move the axis of revolution, in this case y equals negative 2, to the x-axis. Similarly, it might be a good idea if we were doing something with respect to y to translate everything to the y-axis. Okay. I think that does it for this video. Thank you all for watching. As always, let me know how I can help you succeed in this final week, and I will see you in my final